In this video, we're going to take a look at modeling with linear equations. Now, I'm saying this video is about modeling with linear equations. Other books will use different language. Other people will call these types of problems word problems, or like we do in our book, they call these types of problems modeling. You'll also see the phrase application problems, and there's other phrases as well. Whatever language you use, the goal is going to be the same thing. The goal is going to be to create a mathematical equation for a specified scenario, and then use that equation to solve for some unknown values. Now, we may create multiple mathematical equations for a specified scenario, or we may end up just having one math equation. Now, in our book and in lots of other books, they lay out steps for doing modeling or steps for solving word problems. In general, the steps go like this. We're going to have to understand the problem. We're going to have to determine what variables we're going to use. We're going to have to create the mathematical equation or the equations. And then we solve that equation so that we solve for the problem that's asked. Once we do that, then we'll give the final answer or the final answers. Now that's all very, very general because there's so many different types of mathematical equations that can come up and so many different types of scenarios. Even in the context of linear equations, there's a lot of different types of scenarios. Specifically, because there's a lot of types of word problems, we'll break it down into kind of two types. One is where we create equations using information from the problem and logic. And that's like finding linear equations like we did in a previous video. Other times we can be given the equation or the equations to use. Either way, we utilize the same techniques. So let's jump into an example. This example says a rental company charges $72 per day plus a $120 drop-off fee for an item. So if we want to rent that item, it costs $72 for every day that we rent it, plus an additional $120 drop-off fee. It's asking us first to create an equation for the cost to rent the item for a specified number of days. And notice that it wants us to use capital C to denote the cost of the item, cost of the rental, and lowercase d for the specified number of days. Now we'll do that, and then we'll use that equation to answer these two problems. Specifically, we'll calculate the cost for a 14-day rental, and we'll figure out how long we can rent the item if I have $400. So hopefully we all understand that we're talking about renting a certain item. We already know what the variables involved are going to be. This type of a problem is a fixed plus variable cost. We have a fixed cost that's the $120 drop-off fee. And then we have a variable cost, which is the $72 per day we rent the item. Now, using logic, that means the total cost, which is C, is going to be that $120 drop-off fee plus $72 times the number of days that we rent. So the equation for the cost of the item for a D-day rental will be 120 plus 72 times D. Now, it doesn't matter the order that you write that. You can write cost is equal to 72 times D plus 120. That's the same equation. So whichever one you'd like to write, whichever way you'd like to write it, it's the same equation. And notice that this is a linear equation. It's like y equals m times x plus b. We just have c and d rather than y and x. Then it asks us to calculate the cost of a 14-day rental. All we have to do is input a 14 into the d for number of days. Doesn't matter which equation you use, the first or the second. Again, they're both the same. And when we take 72 times 14 and then add 120, I get 1,128. When we answer the question, usually we want to write our answer to a word problem in a short sentence. So all we have to say is the cost to rent is, and then I'd put 1,128. And I'd put the label on if I'm actually answering the question. So cost to rent is $1,128. That's the answer to this question. Now we can say, how long can we rent the item if we have $400? Well, if I have $400, then my cost at most is 400. Some people use an inequality for this, but I generally just write the equal sign and then solve for D. If I take 400 minus 120, because I'm going to have to subtract 120 from both sides, I'll get 280 is equal to 72 times D. Solving for D means I divide both sides by 72. I won't show that step, but I get 3.8 repeating as my D. So 3.89 if I round to 2 decimal places. Now here's where it gets a little bit tricky. If I'm going to answer this question, it kind of depends on the type of rent that is allowed. If I can rent this for a half of a day, then I could rent this for 3.5 days. If I can only rent this for whole days at a time, then I could only rent for 3 days. If I can rent for partial, if I can get very specific, I could say, well, we can rent this up to 3.88 repeating days. So right now, I'll say we can rent for up to 3.88 repeating. I'll just round that to 2 decimal places, days. Again, depending on the type of rental that's allowed, it might be able to just be rented for whole numbers of days, in which case you'd only be able to rent for 3 days, because if you rented for 4, you'd be over 400. So that's what we're doing with modeling. And again, this was a fixed plus variable cost. Whether you use this equation, this first one, or the second equation is up to you. Whichever you feel more comfortable with is perfectly fine. Let's take a look at another example with a fixed plus variable, not cost in this case, but fixed plus variable salary in this case. Let's say two jobs are being offered to a salesperson. The first has a base salary of $45,000 with an 8% commission. That means on everything that this salesperson sells, he gets 8% of the sales. The second job has a base salary of $75,000 with a 4% commission. Create an equation for the total salary, which we'll call S, for each job if the amount of commission sales is C. Now we're going to have to actually create two equations because there's two jobs here. So we're going to create an equation for each job. So two equations total. And then what we'll do is we'll figure out how much the total salary in each job is if the salesperson has $250,000 worth of sales. And then we'll ask how many sales or how much in sales does the salesperson need to make so that the total salary of both jobs is the same. If you want to go ahead and push pause on this video and try this example on your own. In a couple of seconds, I'll show you how it's done. All right, so I'm going to call the first job, job A. And the salary for job A, that's the S, is going to be $45,000 plus an 8% commission. Now, when we're dealing with percentages, we'll have to translate that into a decimal when I put it into an equation. So an 8% commission is 0.08 times the number of the amount of commission sales, which is called C. Again, if you want to write this as 0.08 C plus 45,000 and just swap the order of those terms, that's perfectly fine. Job B has a total amount of salary, which is 75,000 plus a 4% earnings on all the commissions. So job A is 45,000 plus an 8% earnings on commission. Job B is 75,000 plus 4% earnings on commission. So these are the two salaries for each job. Now, in terms of how much in total salary each job gives me, if the salesperson has 250,000 worth of sales, 250,000 worth of sales is the commission sales. So that's the C. And so for job A, whoops, what we would do is we would take that 45,000 and then add on 0.08 multiplied times the 250,000. And that's a pretty straightforward calculation. Just type that into your calculator, 45,000 plus 0.08 times 250,000. You should get $65,000. And I'll just label that right now. So job A would have a total salary of $65,000. Job B, on the other hand, would be $75,000 plus a 4% commission on that 250,000. And again, that's just something you have to type in to the calculator, or a calculator, I should say. When I did that, I ended up getting 85,000. So job B would have a salary of $85,000. I capitalized that. I didn't need to capitalize that. There we go. So that's the answer. Those are the answers, I should say. It would say job A has a salary of $65,000. Job B has a salary of $85,000. If the salesperson has $250,000 worth of commission sales. All right. Now, how much in sales does the salesperson need to make so that the total salary of both jobs is the same? This one's a little bit different. All we have to do is say, well, when the total salary is the same, that means the output of 1 is equal to the output of 2. So all we have to do is set the 2 equal to each other and then solve. We take 45,000 plus 8% of the commission sales and set that equal to 75,000 plus 4% of the commission sales and then solve. The first step would be subtracting 0.04C from both sides. That would give us 45,000 plus 0.04C is equal to 75,000. Then I would subtract 45,000 from both sides. When I do that, I end up with 0.04C is equal to 30,000. And then I would divide both sides by 0.04. If I divide 30,000 by 0.04, that comes out to 750,000. And in answering that question, if I were to try to, answer that question with a sentence, I would say for both salaries to be the same, the salesperson would need to sell $750,000 worth of commission sales. So there you go. Salesperson needs to sell $750,000 for the total salary to be equal in both cases. Now, an interesting little fact here that we saw is that, well, let me go back up to this one. When the sales were 250,000, job B was a better salary. At 750,000, both jobs are equal. And you could figure out that if you sold more than 750,000, then getting the 8% on sales plus the additional 45,000 would be the better option. So job B would be the better option, or excuse me, job B is the better option in smaller sales. Job A would be the better option if they can sell more than 750,000. So there we go. That's the idea of that problem. Now, in both example 1 and in example 2, we had kind of a fixed plus variable cost. So in every equation we got, we ended up with something that was akin to y equals mx plus b. All right. In this case, the slope was the 0.08 and the 0.04, depending on which equation we're dealing with, and the b was 45,000 or 75,000, depending on which equation we were dealing with. But we had S equals to something times C plus another number, or another number plus something times C. In other examples, it won't be quite that straightforward. We won't get the y equals mx plus b look initially. So that happens in example 3. In example 3, I'm going to have to essentially create a couple of equations and then mash them together into one. So example 3 says two numbers add up to 47. One number is 9 more than the other. What are the two numbers? Now, you could probably like guess and check on numbers that are 9 apart that add to 47, but that may take you a little bit. So it's much more efficient to solve this with algebra in the long run if we know some algebra. So that's what we're going to do. Now, whenever we do this, we start out by setting up our variables. And it doesn't matter what variables we call what. If you wanted to use x and y, that's perfectly fine. If x is equal to the first number, then y can be equal to the second number. So we could do that. We could also use letters like A and B. A is the first number, B is the second number. You can use whatever variables you'd like. I think I'll use X and Y for this case. Now, there's actually two relations that are given to us. The first is that the two numbers add to 47. So X plus Y add up to give me 47. That's one equation. The other is that one number is 9 more than the other. I'll call Y the bigger number. So Y is equal to X plus 9. 9 more than the other would be the other number plus an additional 9. Now I have two equations here, and I want to mash those up into a single variable equation. There's multiple ways of doing that, but the way I'm going to do this one is I'm going to take the x plus y equals 47, and then I'm going to replace that y with the expression x plus 9, because we know that y is equal to x plus 9. So I replace that y with x plus 9, and that's the equation I get. That's an equation in one variable. And I can solve for x in this equation. X plus x is 2x, plus 9 is equal to 47. I would subtract 9 from both sides. That means 2x is equal to 38. And then I would divide both sides by 2. When I divide 38 by 2, I get a 19. So I get x is equal to 19. Now that's just the first number, or the smaller number. To find the y, I just plug that x back into this equation. Y is equal to x plus 9. So since x is 19, that means y is equal to 19 plus 9, which, by the way, is 28. Notice that 19 and 28 are 9 apart, And also, if you add 19 plus 28, you get 47. So this is one where we came up with two linear equations and we had to mash them together to get a single linear equation in one variable. And then I can solve for that variable and then figure out what the other variable is. And then lastly, I'll answer the question. Basically, all we have to say is that the two numbers are 19 and 28. The smaller number is 19, the larger number is 28. This technique of replacing a variable with an expression because the variable is equal to the expression in the other equation, this is called a substitution technique. We're substituting this y out for the expression x plus 9. And I can do that since y is equal to x plus 9 in the other equation. Let's take a look at another example. Here it says 3 consecutive integers add to 519. What are the 3 numbers? If you want to try this on your own, push pause on the video. Otherwise, in a couple of seconds, I'll show you how it's done. All right, so 3 consecutive integers adding up to 519. We'll call the 3 numbers A, B, and C this time. So since they add up to 519, we get A plus B plus C is equal to 519. Now here's the real trick. Because these are consecutive integers, that means they're in a row. So if A was 3, then B would be 4, and C would be 5. So consecutive means one right after the other. And that means if I call A the smallest number, then B is going to be one more than the smallest number. And C is going to be one more than that. One more than B is like 2 more than A. So C is going to be like A plus 2. Now I can do the substitution technique with that first equation. I have A plus B plus C is equal to 519. And now I can replace the B with the expression A plus 1. And I can replace the C with the expression A plus 2. Now those parentheses don't do much other than symbolize where things went. Since the coefficient in front of those parentheses is 1, we can just drop the parentheses and we end up with A plus 1 plus A plus 2 is equal to 519. So that's 3 A's plus 3 is equal to 519. Then I'd solve for A. If I take 519 and subtract 3, I get 516. That means 3 times A is equal to 516. Then I can divide by 3 on both sides, and that would give me A is equal to 172. 172. Now remember, that's the smallest number. If I add 1 to that, I get B. So B would have to be 173. And if I add 2 to 172, I get 174. That would be C. So to answer this question, we would say the three numbers are 172, 173, and 174. Again, that's based off of doing this substitution technique. And knowing the fact that consecutive integers means that if I have a smallest, the next one is one more than that. The next one is two more than the smallest. Again, you can do this by guessing and checking, but the algebra is really nice to use in these types of cases. And so that's why we utilize the algebra techniques. Another place these sort of techniques can be used is with basic geometry formulas. So in this example, it says the perimeter of a rectangle is 213 feet. If the length is 5 feet more than the width, what are the dimensions of the rectangle? In this case, obviously, we need to know what the perimeter of a rectangle is. The perimeter of a rectangle is going to be twice the length plus twice the width. That's something that's universal in geometry, so we can hopefully know that. If you don't know that, then you could obviously look that up somewhere. Just Google perimeter of a rectangle, and it will give you the equation. Perimeter is twice the length plus twice the width. So the formula for perimeter is something that we have here. I've written it down as 2L plus 2W. I know the perimeter is that formula, but in this case, the perimeter is 213. So I can replace the perimeter P with 213. And now the other thing that it says is the length is 5 feet more than the width. Be careful when you write this. That means the length is L equals 5 feet more is the width plus 5. So L is equal to W plus 5. And in the same way, I substituted out a variable for an expression. I'll do that in this case as well. 213 is going to be equal to 2 times L plus 2 times W. And I'll substitute that L out with the expression W plus 5. Be careful when you do that, because when you substitute W plus 5 in for L, you need to make sure that the coefficient of 2 is outside of the parentheses. That way, when you simplify that right-hand side, you end up with 2W plus 10 plus 2W, and then I can go on solving. So we'd get 213 is equal to 4W plus 10. Subtracting 10 from both sides would give you 203 is equal to 4 times W. Then you can take 203 and divide by 4. So dividing both sides by 4 gives me 50.75 as the width. If the width is 50.75, then I can add 5 to that to get the length. So let's go ahead and do that. Length is equal to 50.75 plus 5. So the length is equal to 55.75. Now, if you have any doubt that we did this correctly, we could stick it back into both equations. We can see that the length is 5 more than the width. And if I take twice the width, 2 times 50.75 and add twice the length, that's 2 times 55.75, those should add up to 213, which they in fact do. Now, one more thing I want to mention, all of my measurements were in feet. Therefore, when I give my final answer, we would say the width is 50.75 feet and the length is 55.75 feet. So since all of my measurements were in feet, then the width and length also have to be in feet. Again, this is the same concept as the previous two problems, just utilizing a basic geometric formula that we can either look up or we have probably seen before. Now for the next few problems, I'll call these mixture problems. We're going to use the same technique that we did, that technique of substitution, but it's going to be mixtures of things. So in example 6, it says a person invests $5,000 split between two different stocks. That means some of the 5,000 went into one stock and some of the 5,000 went into another stock. At the end of the year, stock A made 8% and stock B earned 12%. If the person made a total of $454.56, then how much was invested into each stock initially? So this person put $5,000 into two stocks, not knowing which one was going to gain more and which one was gaining less. And one made 8%, the other made 12%. We can see that he earned or she earned $454.56. How much was invested into each stock? Let's go ahead and do this one. Now we start by understanding what's going on. Hopefully we understand what's going on. Person puts money into two stocks, they earn different amounts. We have the total earnings, but we want to figure out each individual investment to begin with. And so we're going to label our variables. A is going to be the amount in stock A. And similarly, B is going to be equal to the amount in stock B. Pretty easy on those labels. Now we know that combined, they together end up as $5,000. So the amount in A plus the amount in B is $5,000. And here's where the other equation comes into play. The other equation says A made 8%. So how much was made in A is 0.08 times the investment in A. The amount made in stock B is 12% of the initial investment in stock B. So 8% of A plus 12% of B added up to $454.56. That was how much was made in total. Now, in this case, we may be thinking this is really similar. This equation is very similar to the perimeter equation we had last time. We had 2L plus 2W equals a number. And then I substitute it out for one of my variables. However, I don't quite have the same type of equation because I don't have one variable solved for this initial equation. So that's what I'm going to do. I'm going to rewrite that initial equation. Instead of rewriting it, instead of writing it as a plus b equals 5,000, I'm going to realize that if I subtract b from both sides, 5,000 minus b is equal to a. So a plus b equals 5,000 is equivalent to a equals 5,000 minus b. And now I'm ready to do my substitution. I'm going to take this equation here, 0.08a plus 0.12b equals 454.56, and I'm going to replace a with 5,000 minus b. So let's go ahead and do that. 0.08 times the quantity 5,000 minus b plus 0.12 times b is equal to 454.56. Now I can simplify that equation. If I take 0.08 times 5,000, I end up with 400. So I end up with 400 minus 0.08 times b plus 0.12 times b is equal to 454.56. Now I'm going to do two steps at once. I'm going to simplify that left-hand side. Well, actually, I'll show both steps. Why not? When I simplify the left-hand side, 0.08, negative 0.08b plus 0.12b add together to give me 0.04 times b. Then I have 400 plus 0.04 times b on the left-hand side of the equation. The right-hand side is still 454.56. I would subtract 400 from both sides and get 0.04b is equal to 54.56. And if I take 54.56 and divide by 0.04, because I need to divide by 0.04 to solve that, I get b is equal to 1,364. That's the amount that the investor, he or she, put into stock B. To figure out how much they put into stock A, I would just take 5,000 minus that number. So A, let me give one more step. A is going to be 5,000 minus 1,364. And when I subtract that, I get 3,636. So there you go. That is the numerical answer. To finish this off, I would say the person put $3,636 into stock A and put $1,364 into stock B. And that's technically the final answer, at least to this problem. So here's where we had a mixture, and then we use the other equation, the total equation, rewritten for our substitution. In this case, we substituted in A. Now, other people may have switched this up. Instead of subtracting B from both sides, other people may have subtracted A from both sides and did a substitution and replaced B with 5,000 minus A. If you did that, what you would do is you'd solve for A and you'd come out with A of 3636, 3,636. Either way is fine. Here's another mixture problem. This time, instead of dealing with a mixture that is money, this time the mixture is going to be acid or alcohol solutions, excuse me. A person has two solutions of alcohol. One solution is a 10% alcohol. The other solution is a 3% alcohol solution. He wants to combine these two to make a 450 milliliter solution that is 8% alcohol. How much of the 10% and how much of the 3% should the person mix in order to get such a solution? So we're pouring two solutions together to create something in the middle. And this is a very classic mixture type problem. We're pouring two things, one's a 10%, one's a 3%, to get a 450 milliliter solution that is 8%. So similar to the last problem, we have two amounts that we're combining and making a third thing. So we have a 10% and a 3% amount that we're pouring together to make 8%. Now, just by logic, you'll probably have to add more of the 10% and less of the 3% in order to get an 8%, because 8% is closer to 10 than it is to 3. But how much of each is the issue? So here's what we can do on problems like this. We're going to once again set up two equations. The first is going to be the total amount of liquid equation. The total amount of liquid that we're adding is A plus B. And that's going to add to a total amount of liquid of 450 milliliters. So that's the total amounts equation. The second equation is this. It's the percent of alcohol or the alcohol content equation. Since the A is 10% alcohol, that means 10% of A will be alcohol, 3% of B will be alcohol, and that will combine in such a way that 8% of that 450 milliliters will be alcohol. So these are the two equations that I'm going to be dealing with. A plus B is equal to 450, and 0.10A plus 0.03B is equal to 0.08 times 450. Now there's multiple ways of solving this. A little bit later on in this course, we can use elimination to solve this. But since we've been doing substitution, I will do substitution once again. I will subtract B from both sides and get A is equal to 450 minus B for that first equation. So the first equation is equivalent to A equals 450 minus B. And then I can substitute that expression, 450 minus B, in for A. So let's do that. 0.10 times 450 minus B plus 0.03B is equal to, now I'm going to multiply that out. 0.08 times 450 is 36. So that's what we end up getting. Now we can distribute that 0.10. We can combine like terms. We can solve. We can do all of those things with this equation. I'll go ahead and simplify that pretty quickly. So 0.10 times 450 is 45 minus 0.10 times b plus 0.03 times b is equal to 36. I'd combine like terms. When I do that, I would end up with 45 minus 0.07b is equal to 36. Then I would subtract 45 from both sides. That would give me a negative 0.07b is equal to negative 9. And then when I divide both sides by negative 0.07, I get b is 9 divided by 0.07. That, by the way, as a fraction is 900 over 7, which does not actually come out to a really nice decimal. It's about 128.57. But that's fine. Sometimes the amounts you need to mix are not really nice, perfect whole number amounts, just like in this case. Now, the A is going to be, if I'm exact, it's going to be 450 minus that 900 over 7. If I wanted to approximate, I could use 128.57. But if I do the subtraction, if I wanted to be exact, I'd be at 200, not 200, 2,250 over 7. If I wanted to be approximate, it would be approximately 321.43. Remember, A was the amount of the 10% and B was the amount of the 3%. So in this case, what we should say is we should mix about 321.43 milliliters of the 10% with about 128.57 milliliters of the 3% solution. And that would give us 8% solution, and it would give us 450 milliliters of that. Now, there's one other scenario that I do want to cover before I move on to some other scenarios other than these types of percentage mixture problems. So here it is. A chemist accidentally orders and receives a solution that's 300 milliliters of 12% acid. The chemist wants a 7% acid solution. How much water should the chemist add to create a 7% solution? How much of that 7% solution will the chemist create? So in this case, instead of adding two percentages together, we're just going to add water to a certain mixture and dilute it to a weaker mixture. So we're going to take this 300 milliliters of 12% acid, add water, and then dilute it to a weaker acid solution. If you want to try this on your own, push pause on the video and set up the equations and try this on your own. In a couple of seconds, I'll show you how it's done. Now, my two key variables in this case are going to be the amount of water that I want to add, and then the final amount of that 7% solution that I'm going to get. If we're going to set this up? We set this up just like the previous problem. We'll have two equations. One is a totals equation. And in the totals equation, I'm taking that initial 300 milliliters that I have, and I'm going to add water to that to create whatever the final amount of that 7% solution adds up to. So that's the total amount of liquid equation. Notice that one's already set up for substitution. 300 plus W is equal to F. The other equation is going to look like the percentage of alcohol equation in the previous problem, except for this time the percentage is acid. So we're going to have 12% acid, the 12% of 300 milliliters, that's what I have. We're going to add water to that. By the way, water is 0% acid, so that's not going to affect anything. And that is going to add up to a 7% final amount. Now, notice what's going to happen here. When I have 0 times any variable, that variable is going to drop out. So technically, I don't even have to do substitution. Even though we're set up for substitution, I could replace the F with 300 plus W. Because I'm adding 0% acid with the water, this second equation is just 0.12 times 300, that's 36, plus 0% acid in the water, is equal to 0.07 times F. And I don't even need to do a substitution at this stage. All I would have to do to solve is to divide both sides by 0.07. If I take 36 divided by 0.07, I get about 514.29. By the way, that's 3,600 divided by 7 as an exact amount. And that's approximately, like I said, 514.29. So that's the final amount of liquid that we are going to have. How much water do I need to add to that? Well, I can find that out by plugging the 514.29 into there. Or you can plug in the 3,600 divided by 7 if you want an exact amount. So all we have to do is plug in 3,600 divided by 7 and then subtract 300 from both sides. If I do that as a improper fraction, I would get that the amount of water I need to add is 1,500 divided by 7, and that's approximately 214.29. That would be in milliliters. So what this is telling me is that in order to dilute this 12% acid mixture that I have, I can add 214.29 milliliters of water, and that will give me 514.29 milliliters of a 7% acid solution. Let me write that down in a sentence. That sentence would state, add 214.29 milliliters of water to the initial solution to create a 514.29 milliliter solution that is 7% acid. So this is one that I wanted to show because even though I can set it up with two equations, having that coefficient of 0 is really nice because it eliminates one of the variables, the variable w in this second equation. And I can solve for my final amount. And then I can plug that back in and solve for the w. So hopefully that makes sense. This one is a little bit easier because we have a 0% acid. Water is 0% acid. So we see that in example 6, 7, and 8. These are kind of percentage mixture type problems. And there's a few different examples of percentage mixture type problems that we can solve using linear equations. Now let's move on to a different type of problem, one that looks like example 9. In this example, it says the salary of an employee is growing at a constant amount each year. In 2015, when they were hired, they received a salary of $56,000. In 2025, they received a salary of $78,000. Create an equation describing this employee's salary. And then we'll ask how much is the salary growing per year? How much will their salary be in 2030? And when will their salary be $100,000 or more? Now, in this case, we have essentially two different points of salary, and we know it's growing at a constant amount each year. Growing at a constant amount means that we're getting a linear equation. If I know the salary in 2015 and I know the salary in 2025, that's like having 2 points on a line. And so I can create an equation describing that employee's salary based on knowing 2 points on a line. And then we can create the line giving us that salary. Let's go ahead and do that. Now, when we do that, we have to decide what types of points we're going to be using. We could either write time as in years, calendar year. So if we go time as in a calendar year, then 2015 will be T equals 2015. So if I'm talking about calendar year, then the points are going to be 2015, that's the year, comma, the salary of 56,000. And then the other point will be 2025, comma, the salary of 78,000. Now, other times, people might not want calendar year to be the time. Other times, people will use the time as the years since hiring. In that case, then because they were hired in the year 2015, we'll use 0 to represent the year 2015. And then the salary of 56,000. 2025 would be 10 years after they were hired. So that would be 10 and then 78,000. So you can use either of these two pairs and create a line or create an equation. We just have to pick a track and stay on it. I don't want to mix and match different time periods or different ways of calculating time. It's probably going to be easiest to use time as years since hired, but we don't have to. I'll show you both ways, but again, I would tend to use years since hired as my time. So if I do that, let's say T is equal to the years since hired. Then I could find the slope of that line by the change in Y values, 78,000 minus 56,000, divided by the change in X values. That's 10 minus 0. So the slope of that line would be 22,000 divided by 10, which would be 2,200. Hopefully that makes sense. 22,000 divided by 10. And then I'll call it salary. I'll use S for that. So the salary will be equal to the slope times, again, I use the T instead of X value, so I'll use T as time since hired, plus the B value that I don't know. And then I can plug in a point. The easiest point to plug in is 56,000, because when I plug in a 0 for T, and a 56,000 for S, then the value of B is obviously 56,000. That's the advantage, that's one of the advantage of using this system where T is the years since being hired. So now I can create an equation that describes this employee's salary. The salary is going to be equal to 2,200 times T plus 56,000. Now, by the way, if you used time as in calendar year, everything would be similar. Let me go ahead and do that, but a little bit different. So if we use calendar year, we would use these 2 points where 2015 is the initial T value and 2025 is the second T value. When I subtract, I would subtract 2025 minus 2015. Notice that's still 10. So the slope is still 2,200. But in this case, I'd have to type in 2015 as your T and then solve 2015 times 2,200 becomes 4,433,000. So B would end up, when you subtract, would end up being negative 4,377,000. And notice that's just not as nice of a number to deal with. You could deal with that number. You could deal with the equation S is equal to 2,200 times T minus 4,377,000. But it's not as nice of an equation to deal with as the previous one. So that's why oftentimes it's a lot easier to use T as years since hired than it is to use calendar years. So this is what I'm going to base my answering of the next few questions on. I'm going to use years since hired as the equation I use. Time is years since hired. The questions that we were asked to solve were the following. How much is the salary growing per year? That's the slope of this line. That says the salary is growing at $2,200 per year. And then it says, how much will their salary be in 2030? Now, be really careful about this one. Since we're using time since hired, and they were hired in 2015, 2030 will be 15 years after they have been hired. So 2030 is a time of 15 in this case. But once I know that, I can simply plug in 15 for my t and solve that equation. Their salary will be 2,200 times 15 plus 56,000. And that's $89,000. And that's what we would answer. We would say their salary will be $89,000. And lastly, when will their salary be $100,000, or we could safely say or more? Well, if we were looking for a salary of $100,000, I just replace the S with 100,000 and then solve for T. Subtract 56,000 from both sides. 100,000 minus 56,000 is 44,000 is equal to 2,200 times T. If I take 44,000 divided by 2,200, I get a T of 20. So that's what we end up getting. Now, this T of 20 is 20 years after initial hire. So that is the year, since they were hired in 2015, 20 years after that would be 2035. So they'll have initial a salary of $100,000 in the year 2035. This came out as a really nice year. Obviously, if our time period came out to 20.2 or 20.3, we would say, well, it's under that, under the salary of 100,000 in the one year, and then the next year it'll be over 100,000. So this one turned out to be nice, but others may not. By the way, you can answer all three of those questions using this other equation as well. It's just messier. It has a messier B. But you could plug in, for instance, 2030 and see that you get the same answer as we did for this one. You could plug in 2030 and find the salary in 2030. You could plug in $100,000 for the salary and then solve it and figure out you get the year 2035, just like we did in this example. So there we go. Here we used essentially 2 points, and it was easier to use time as the years since hired instead of calendar years in this case. Let's look at another example. Here's example 10. It says a pond has a net inflow of water of 500 cubic feet per year. So that means some water's coming in, some water's coming out, but more water is coming in than going out. And there's 500 cubic feet more water coming in per year than moving out. In the year 1990, the pond had 352,400 cubic feet of water. It says create an equation describing the amount of water, we'll call that W, in the pond where T is the number of years since 1990. So we'll call T of 0, 1990, and then every other year we'll just tack on 1 to the T. After you do that, then answer these 2 questions. How much water will be in the pond in 2040 if this trend continues? And when will the pond have at least 375,000 cubic feet of water? Go ahead and push pause on the video and see if you can create this equation and then answer those 2 questions. After you do that, in a couple of seconds, I will show you how that's done. So here's the problem on a single page. Now, we're going to create an equation describing the amount of water in the pond where T is the years since 1990. So water in the pond is going to be some slope times years since 1990 plus base value. If we are looking at the text of this problem, since T is the years since 1990, and we know the pond had initially in 1990 352,400 cubic feet of water, that means we're essentially giving the point 0, 352, 400. Let me actually write it this way so we can see it a little bit better. So that's like saying the line is going through this point and the net inflow is 500 cubic feet of water. That's telling me that the change every year is 500, is a positive 500. So essentially I have the slope and I have the y-intercept given to me. So the slope is 500. We'd go W is equal to 500 times T plus B. When I plug in 0, 352,400, I get a B of 352,400. I won't even bother plugging in and doing the algebra. So the equation that I'm getting is that the amount of water is equal to 500 times t plus 352 400. Hopefully we can see that as well. Now, if you can do that all in your head and come up with this equation in your head, that's fine too. I like writing out all the steps on the video to show you all of the steps, but if you can come up with that in your head using just logic and inference, go ahead and do that. Now, the next question says, how much water will be in the pond in the year 2020 if this trend continues? Before we do anything, we need to figure out that since T is years since 1990, 2040, excuse me if I said another number, but 2040 is 50 years since 1990. So that's a T of 50. And I can just plug in 50 for T and then calculate how much water will be in the pond. We take 500 times 50 plus 352,400. That is 377,400. So there will be 377,400 cubic feet of water in this pond in 2040. If this trend continues, obviously. Now, the other thing it says is when will the pond have at least 375,000 cubic feet of water? So in this case, I plug in 375,000 in for the W. That's going to be 500 times T plus 352,400. And now I can solve that for T. I'd take 375,000 and I'd subtract 352,400 from each side of the equation. When I take 375,000 minus 352,400, I end up with 22,600 on the left-hand side of the equation. And on the right-hand side of the equation, I end up with 500 times T. I would divide both sides by 500 to get a T of 45.2. Now, in this case, it makes sense to say that the year we will reach 375,000 is slightly after 45 years past 1990. If I go 45 years past 1990, that is the year 2035, and technically it'd be 0.2 into the year if we had a constant rate of inflow. So sometime in the year 2035, it will hit 375,000 cubic feet of water. Sometime just after the year 2035. Hopefully that all makes sense. In this example, what was happening was we were getting essentially a slope given to us and going through a point. In the previous example, it was creating a line going through 2 points. And that's just like things we worked on in a previous video. For the last example in this section, we'll do one where the equation has already been given to us. It turns out that we can find the equation for converting temperature in Fahrenheit to Celsius and from Celsius to Fahrenheit. That's given below. And we can look this up, or you could figure it out through some data. You could Google it, you could look it up, but this is a very well-known linear equation. The degree in Fahrenheit is 9/5 times the temperature in Celsius plus 32. So if we asked, what is the temperature in Fahrenheit when the temperature is 16 degrees Celsius? We could find that answer by utilizing this equation that's been given to us. We could say, what's the temperature in Fahrenheit when the temperature reads 31 degrees Celsius? We could say, what's the temperature in Celsius when the temperature reads 75 degrees Fahrenheit? We could say, what's the temperature in Celsius when the temperature is 160 degrees Fahrenheit? And when are the two temperature measurements equal to each other? In other words, what degree Fahrenheit is equal to the same number degree in Celsius? Why don't you try to do all of those types of questions? Here they all are laid out in one sheet. So this should be fairly straightforward because we don't have to find the equation. The equation is already given to us. So now we don't have to go through all the trouble of creating equations. We just have to use the equation itself. Go ahead and push pause on this video and try to do this. In a couple of seconds, I'll show you how each of these problems is done. All right, so let's do temperature in Fahrenheit when the temperature is 16 degrees Celsius. So what I would do is I would say F is equal to 9/5. I would plug in a 16 for my temperature in Celsius and then plus 32. If we do 9/5 times 16 and then add 32, you get a temperature in Fahrenheit of 60.8 degrees. So the temperature would be 60.8 degrees Fahrenheit. Well, what if the temperature were 31 degrees in Celsius? By the way, if somebody says centigrade, centigrade and Celsius are the same concepts. So here we have F is equal to, again, I just take 9/5, type in 31, and then add 32. So 9/5 times 31 plus 32, and that would become 87.8 degrees Fahrenheit. So 87.8 degrees in Fahrenheit. And if you wanted to label, you just put that degree Fahrenheit label, just this one. The little degree is a little O on the upper right. And you could, tack on that label to any degree Fahrenheit that you wanted to. Then we could do the reverse. We could find a temperature in Celsius if the temperature were 75 degrees Fahrenheit. So we type in the 75 in for the F, and then we'd have to use some equation solving to solve for C. In this case, we'd take both sides and we'd subtract 32. When I subtract 32 from 75, I get 43 is equal to 9/5 times C. And then you divide by 9/5, or you could multiply by the reciprocal of 9/5, which is 5/9. So if I multiply by 5/9 or divide by the fraction 9/5, I get about 23.89, which is 23 and 8/9 degrees Celsius. So we get 23 and 8/9 degrees Celsius. All right, for your C, sorry. If you wanted to, you could also give an approximate value of 23.89 as your approximate degrees in Celsius. Be careful when you divide by fractions. If you take 43 divided by the fraction 9/5, make sure that there's parentheses around that fraction when you type it into your calculator. We can do the same thing when the temperature is 160 degrees Fahrenheit. 160 is equal to 9/5 times C plus 32. We would take 160, and on both sides we'd subtract 32, but on the left-hand side I'd get 128. On the right-hand side I'd get 9/5 times C. Then I would divide by 9/5. Make sure when you type that in, that's in parentheses, and you get essentially 71 and 1/9 degrees Celsius. Again, if I wanted to label that, I just put the little OC there, and there we go. So be careful here. If somebody says it's 71 and 1/9 degrees out, well, if they're talking about Fahrenheit, that's just fine to go outside 71 and 1/9, a little over 71 degrees. But if we're talking about Celsius, then 71 degrees is really, really hot. Like you would not want to go out in 160-degree Fahrenheit heat. Now, lastly, it says, when are the two temperature measurements equal? The way we can solve this is saying, when is F equal to C? When is F equal to C? The way we can determine that is by substitution once again. Just plug in F for C or C for F, doesn't matter which way you do it, in this other equation. I'll replace this C with an F, and so we'll get F is equal to 9/5 times F plus 32. At this stage, we would subtract 9/5 times F from both sides. This is 1F. 1 minus 9/5 is a negative 4/5. So we'd end up with negative 4/5 times F is equal to 32. By the way, if you didn't like this denominator of 5, you could clear that out by multiplying everything by 5. At this stage, I would divide both sides by a -4/5. When I do that, on the left-hand side, I get f. And on the right-hand side, I do 32 divided by -4/5. And when I type that into my calculator, I would get a -40. If I plugged in -40 for f, then that would mean c would be -40 as well. And when you plug in -40 for c and multiply times 9/5 and then add 32, you'd get a -40. And you'd end up with -40 when you plug in c gives you -40 for f. And when you plug in -40 for f, you get a -40 for c. So -40 degrees Fahrenheit is the same temperature as -40 degrees Celsius. Let me write that down. So -40 degrees Celsius is equal to -40 degrees Fahrenheit. I need the label here. I guess I could have just typed that in, but it's nice. So there you go. Fun fact, -40 degrees Fahrenheit is the same temperature as -40 degrees Celsius. Again, that one was really nice because the actual equation was provided for us. Most of the time, we're going to have to create the equation through logic and the types of techniques we saw earlier on creating linear equations. So this section dealt with linear models, where we had our models that involved linear equations. We saw a lot of different techniques in this. You can go back and look at some of those techniques, like using substitution. We did percentage mixture problems. We did a geometry type problem. We came up with a linear equation using 2 points. We came up with a linear equation knowing the slope in a point. But it was all linear modeling. In later chapters, we'll see other types of equations that are not linear. And we'll see even more examples that are linear. So we'll see both linear modeling and nonlinear modeling in equations later. Hopefully that all makes sense. That's the end of this video. And this video was on a lot of different linear modeling.